Here we go. So tonight we're going to cover, hold on a second while I get this. Here it is here. We're going to start, oh, phooey. How does this thing?
What do you want to do?
I wanted to put it into slideshow mode. Hold on, let me just go do that.
This is blinding me. I'm going to turn this off for a moment.
Here it is. Oh, but now when I do this, oh, I see what the problem is. Hold on, I'm going to go down here. This is how I'm going to do it. Yeah, here we go. Everybody see this?
Oh, yeah, there you go.
Yep.
Okay.
So we're going to talk about the focus here is when you go into
So mushy, I can't even put it in there. Look, you gotta do something about it.
What?
You gotta do something about
Yeah,
this. You say that every night.
okay. So what we're going to do here, when when you go into meditation, and if you can go deep enough and focus, you'll be able to enjoy a number of things that some people call clairvoyance, where they can see very clearly into the microcosm or into the far reaches of space. And in doing this, undoubtedly, a lot of people did this, but they didn't have a framework such as Western science provides for what they were seeing. They'd observe these things and they say, that's nice, and that's nice, and okay, but so what? So we're going to focus here on going after what we call the atom, and we'll come to that in a second. But the basic idea here is on the bottom right, we have a picture of the tree of life of the Kabbalah. We have the Sri Ranta of Hinduism. We have the I Ching here. And then we have a lot of, I'll just say, sacred geometry here. And all of that is focusing on something that modern physics calls strings. These are vibrating strings that capture energy. Energy resonates inside this. And so some people would view this, you have different types of strings, different types of resonances, and that leads to different types of phenomena or different, and some of these things appear to behave like particles, but they're still strings with some energy vibrating inside them. And what's new, what's happened over the last several decades is it appears it's all driven by algorithms, that there's actually algorithms that govern how everything behaves. And this is summarized here by a set of rules, and the rules connect everything in the universe together. So it's a very different view than these views of before. This is a much more modern, I'll just say, computer view of what's underlying everything, what's going on here. So let's get into this and see. we're going to follow a timeline, and I'm just going to, along the way, touch on things that were missed by Western science, culminating in what in 1975 physics called the Standard Model. And they basically hit the wall in 1975, and there's been no real advances in this, with the exception in 2012 when they discovered experimentally the Higgs boson, which was postulated as part of the Standard Model, but people already knew it was there. So physics is sitting here at a crossroads where they've been going at it. They have the best and the brightest, and they've been nowhere for the last 50 years. Okay, but there's some other people before them that did a lot of interesting things, as we'll see. So the timeline we're going to focus on here is really looking at what Democritus called atoms. He said all matter is made up of atoms. Now, this is just something that he said. I couldn't find any evidence or any reason to believe how he came up with that. But if you start with that, then you start to ask yourself, well, if things are made up of atoms, you know, and there's different types of things we see around us, then like the only difference is there might be different types of atoms. And what happened over time was people realized that the atoms themselves were made up of even smaller things. And so that's what we'll focus on, is what are the smaller things that atoms are made up of. But the idea of everything made up of atoms is really, you know, a really fundamental idea, and that really has governed how a lot of Western science evolved over the last 200 years. We're going to deal with, we get to 1803, we have the first experimental evidence that there are atoms. There wasn't anything from, from, you know, for over 2,000 years. It was just a theory. And then we start to get more and more things happening, both experimental and theoretical, that we're going to walk through here. So we're going to go through each of these one at a time, and you'll see what's going on. Here is just what happened kind of in the 20th century, with a lot of different activity taking place we're going to cover. And at the very end of it, just in 2020, we're going to have an unusual individual, Stephen Wolfram, who's going to try, as a physicist, he's going to try and come up with an algorithmic description of physics and the laws that govern what's going on, which is going to lead to things like atoms. So we'll see. So the first one we've got here is Democritus with his atomic theory. And he simply stated that atoms and the vacuum were all there was, that there's atoms, and then the space between the atoms he just called vacuum, and you know, end of story. Now, this was a translation done in 1853, and it's just stated as his principal doctrines. There's no reason to believe, you know, where he got this from, but he felt that they were physical, but they were indivisible. Okay, that these are the basic things that make up everything around us. They're indestructible. They've always been there. They always will be there. And there's a lot of different types of atoms, and they differ in all kinds of shapes and sizes. But that doesn't take away from the fact that everything is made up of atoms. So by and large, this is true. It's an amazing assertion. Sit there and just do this. So let's go here to the first person, John Dalton, who actually came up with some experimental evidence that what are things that are called elements now are all made up of atoms. So the notion of elements, Dalton was a chemist, but he started to realize that, for example, the air was made up of primarily nitrogen and oxygen, or there's other elements that we're familiar with, such as carbon or iron and so forth. And these elements appear to be really fundamental in terms of making everything up from the point of view of a chemist. So he started staring at this, and he started to realize, for example, when you take hydrogen and oxygen and you try and combine them as gases to end up with what we would call water, in whatever form it is. It could be a gas, it could be a liquid. That this occurs in a certain ratio. That the hydrogen itself is always available in atoms, but you don't end up with hydrogen per se existing. You end up with hydrogen bonding with hydrogen is what's actually stable when we actually play with it. So there's two hydrogen atoms, and then there's oxygen, but oxygen has the same issue. It's very reactive, so you end up with two oxygen atoms combining with one another. And when you combine a hydrogen molecule, which is two atoms of hydrogen, you need two of those to get a combination with oxygen to get water. And that's why we call water H2O, because for every one atom of oxygen, there's two atoms of hydrogen. So Dalton was one of the first people to realize this. And this started to lead him to say, well, then this is going to be evidence that there really are things called atoms here, that they're combining in this way. They're all going to have different sizes and masses and properties and so forth. But experimentally, he started to show that these elements, in fact, really the atoms here couldn't be subdivided, they couldn't be created, they couldn't be destroyed. They really were the real basis for what we call modern chemistry. So that was a huge step that happened here. Dalton actually, I believe, is a Unitarian, and came to the United States because he was being persecuted in Europe. Now, the next person that comes up on this timeline is Michael Faraday. Michael Faraday was an incredible English experimentalist, and he gave very, very compelling talks every Christmas time on some aspect of his experiments that he was doing. And these talks have continued today. If you go to London around Christmas time, you'll see these Faraday lectures there. So, but he did a huge amount of popularization of experimental science. So Faraday was the one that most people are familiar with, or one of his demonstrations was, you take a bar magnet and you place a piece of white paper over this bar magnet, and then you sprinkle iron filings onto the white paper, and the iron filings will group together so that they form lines of iron filings. The filings get connected to one another, and they go from one pole of the magnet to the other pole of the magnet, which is underneath the piece of white paper. And so he was showing here that magnetism really exists, and that there's something intrinsic about its properties that is able to create these lines of force that control these iron filings that are there. So when Faraday was doing all of these things, he concluded that there was something related to electricity which was of a fundamental nature. And he basically concluded there was something that we would call today an electron that existed there. It's a fundamental particle. It has a charge associated with it, and so forth. Now he carried out all kinds of experiments trying to investigate electricity. One of the things that was key here was that people had ideas. Well, there's positive electricity and there's negative electricity, and they combine in different ways. And he was able to show that if you simply had a single type of electricity, that would explain everything. You didn't need all of this other stuff that people were coming up with. And in fact, the person that first came up with these ideas was Benjamin Franklin back in the 1750s, when he was flying his kite in thunderstorms and observed that that lightning bolts generated electricity here. So Faraday was absolutely essential in the experiments that he put together that were very systematic. Other people weren't nearly as systematic as Faraday. Faraday's experiments could be all replicated, and this led a lot of people to believing that there really was something there of order for electricity and for magnetism. Now, one of the things that Faraday did that was probably the most important economic thing that he ever did was he took two coils of wire, and he put a piece of metal, some iron, in between, running through each of the coils. And then he put a pulse. This happened almost accidentally. He threw a switch, and that allowed some electricity, some current to flow through one of the coils. And he observed that the other coil, by itself, also this induced a current in the other coil, even though he didn't put anything into it. It coupled mutually from one coil to the other, and this is the basis for how we generate electric power today. We take something that for example, we spin water through a turbine, and the turbine has a lot of coils wrapped around it, and then those coils are coupled into other coils that aren't that are right next to it in the turbine, and that generates electricity that we get when we go plug our electric appliances into wall sockets in our houses. So when Faraday did this, he realized that it was of incredible importance, this ability to induce this electric conduction there. And a reporter came running up to him, having heard Faraday was really excited over this, and he said, "Well, what good is it?" And Faraday said, "I don't know what good it is, but I do know that one day you're going to go tax this." And sure enough, that came true. We get to pay taxes whenever we have our electric bills show up. So that was who Faraday was. I would say he would be the sort of person that would get about 2 or 3 or 4 Nobel Prizes for the work that he did. It was just incredible. One of the problems that Faraday had was he wasn't nearly the same mathematical theoretician that he was the experimentalist. The experiments were beautiful, but he couldn't figure out how to come up with some theory to go explain what he was seeing. And that's what we'll come to with other people, that we're better at doing this. Now, one of the people that you'll never find, but you'll find it here in this class, is someone called Hermann Grassmann. Now, Grassmann, if you just read this, was what's called a polymath. He did many different things. So he was a linguist, he was a mathematician, he was a physicist. He had all kinds of ideas, but the main thing about him was that his work in mathematics was really not noted by anybody until Grassmann was in his 60s. Okay, notice that he died, not just at this stage where people started to realize what he had done in math. Okay, but the main thing that he's known for is coming up with the concept of what we would call a vector space. So just to be concrete in what he did, we have 3 dimensions around us: up, down, right, left, and back and forth. And so since we have 3 dimensions, we actually have 3 one-dimensional vector spaces. That is, each one of these spaces that we have, we can move back and forth on a straight line in that space. We can move up and down, we can move right and left, we can move back and forth. But we could also have a 2-dimensional vector space where when we go up and down and back and forth, that could form a sheet. So you have a 2-dimensional vector space going with a 1-dimensional vector space, which is in and out. And then we could have the full-blown 3-dimensional vector space. So these are examples of ideas that Grassmann tried to spell out for people. He said, I can't understand the stuff that you're trying to teach me. It's too confusing to me. So I'm going to go off and figure it all off on myself. And that's what he did. And he did it for a k-dimensional vector space. Now, the other thing that he did, though, was he was trying to get a position at a university somewhere in Germany. And so he put together a report, and a lot of the report was based on what he had done, and for theoretical reasons, a new theory of electrodynamics. And in doing this, he actually was able to summarize theoretically all of the work that many people, not just Faraday, but many other people, Gauss, Volta, trying to think, there's so many people, Ampere, that had done for electromagnetism. Grassmann, just being totally theoretical, came up with a theory that explained all of these things. But the problem was he was so far ahead of his time, no one could understand what he was talking about. So you had Faraday, who was a great communicator. Everyone could see what he was doing. Then you had Grassmann, who was mathematically correct, but no one could understand him, including the other mathematicians. The mathematician Kummer here, that was one of the great mathematicians in Germany at that point in time, and he just said, well, all of this stuff that Grassmann has put together is just gobbledygook. It looks interesting, but it needs a lot of work. So what happened here was, I was asked in graduate school, I was working on my doctoral dissertation, and one of the people on my doctoral committee asked me to take a look at what Grassmann had done. That what Grassmann came up with was he defined something called a gradient. So when you deal in calculus, you look at rates of change. So if you look at the rate of change of something, you have a function and it's going up. So then the rate of change is going up, and then it levels off. So now the rate of change is 0, and then it drops down. So now the rate of change goes negative. So you're looking at this from the point of view of at the rate of change. So what Grassmann did in hindsight was he started off with simply something that we would call a function 3 dimensions of space and 1 of time, 4-dimensional function, and he computed the rate of change of that function in each of the 4 dimensions. In math, that's called, you compute the gradient of the function. That's a generalization of the derivative of the function, which is the rate of change of the function. You do it in each of the four variables that we have here, or 3 for space and 1 for time. But then Grossman repeated it. Once he'd done it for a function, he now had if you will, 4 functions, 1 for each of the space dimensions and 1 for time. And it turned out that in electromagnetism, that's what's called the potential here. When you take the rate of change of the potential, the gradient of the potential, you end up with electric and magnetic fields. And then when you repeat that again, you take the rate of change of the electric and magnetic fields, you end up with the currents densities and sources of currents for electric and magnetic charges and currents. And then when you do that again, you end up back with sources for electromagnetism. So Grossman did all this. It was totally theoretical. I ended up writing it up, and it was published in 1974, which, as you can see, is now 49 years ago. But the thing about this was that this theory that he developed for electromagnetism had nothing to do with physics. It's totally mathematical, and it's just turning the cranks. And so this made me wonder, what in the world was going on here? There's something that's left out of this, because clearly, while it does match what's going on from the point of view of physics, it's also just totally turning the crank. It's just saying, I'll compute the gradient here, I'll compute the gradient there. So what? What's going on? There's something deeper here that got missed. So we'll come back to what that is just shortly, but just keep that in mind. The real key here was in 1861 to 1865, when all of the work that Faraday did, plus many other people, was summarized by James Clerk Maxwell. And he put together a set of equations that describe electric and magnetic fields and how they interact with one another or couple. And it's kind of amazing that one person would be able to take all these things. He looked at all the different experiments that all these different people had done, and he came up with a set of equations, which many people view as the second great unification in physics. The first one had been realized by Isaac Newton when Newton came up with the theory of gravity. Okay, this Maxwell's equations for electromagnetism was viewed as the second huge step forward. And
they're considered somewhat related, aren't they? Magnetism and gravity.
Yeah, magnetism and gravity are definitely related. When I end up having for example, an electron moving through space as a charged particle, it generates an electric field, but it also generates a magnetic field at the same time. And the magnetic field and electric field are coupled to one another, which is what Maxwell described in his equations. So the thing to keep in mind here is what he did. He added one more term that other people had missed in all of their experiments, because he didn't have any experiments to justify it. But in adding this extra term, he felt that the electric and magnetic fields would travel through space as waves, and they'd be moving at a speed. And he thought the only thing that could be doing this is light. And so he proposed that light is really the same as electricity and magnetism. And unifying them, he's predicting that there's the existence of radio waves that we use in our mobile phones all the time. So in this sense, he's also regarded as the founder of modern electrical engineering. Now, the problem with this prediction is that he hasn't seen any sort of evidence for these waves, okay? And remember, the experiments that, for example, Faraday had done and other people were relatively simple experiments that didn't involve anything, in particular, they didn't have things that were vibrating or oscillating at relatively high frequencies, say hundreds of thousands of times per second, 1 million times per second. That's all. Here we go. Here comes Susan.
I was just texting with her. I was gonna tell you.
I'm going to hold off for a second while Susan gets in.
Okay, good.
Sounds
I'm-
like
Okay, thanks, Susie. Start video. Okay,
Hey,
Okay, let me just go back, Susan, so
hi, Susan.
Hi.
you'll see. Yeah, why doesn't this thing go back?
That should do it, I think.
Let me just do this. Hold on. I'm gonna do one thing, take us back to the beginning. Here.
Okay, all right, love you, honey. Okay. Whew. My daughter's here.
Okay,
Okay.
well, that's nice. Takes me back to the same point. Hold on, let me try one more time. Amazing.
She wants me to live with her for 6 months.
Here we go. Okay, I did it. Okay, so now I'm gonna go. Hold on a second.
Okay, that's better.
Okay, what we're talking about, Susan, is when people such as Bruce's brother Ron Cowan went into very deep meditation, they enjoyed certain extra traits, and one of them was the ability to have clairvoyance, to see very clearly into the microcosm and into the far reaches of space. And so we're going to focus here just on the first one, on the microcosm. And what happens there when you deal with the microcosm is you come back to things called atoms. When you drill down, you find that it appears that everything is made up of atoms, and that's let me just skip forward here so you can see what the talk is. So Democritus was the Greek that came up with the idea of atoms, and the problem he had was he simply is saying everything is made up of atoms, just a theory. There's no evidence for this theory, but there was reasons to believe that it was true. The thing that he called atoms, there's simply atoms and there's empty space. That's it. There's nothing else. The atoms are indestructible. They've always been there. And there's a whole variety of types of atoms that make up the different materials that we see around us. But they differ in all kinds of shapes and sizes. And he was pretty much on the money on this, okay? But it took us over 2,000 years to get there, when a very capable chemist, John Dalton, was able to come up with experimental evidence that really elements, and by elements, he realized that there's certain fundamental materials. So oxygen, hydrogen, helium, lithium, carbon, iron. These are actually all elements that are made up of atoms of that are unique to that particular material, and that what goes with it is that they themselves are all of the same size and mass and properties and so forth, but they can't be subdivided or created or destroyed, and they combine with other elements in simple whole number ratios to give us chemical compounds. So the example we used is we take hydrogen and oxygen, but when we combine them, we're going to get water, H2O. Well, the chemical formula for water, H2O, is the immediate tip-off here is when we deal with hydrogen, we can only get hydrogen with atoms paired up. So we get a hydrogen molecule, which is two hydrogen atoms paired up. We never find a single hydrogen atom. If we do, it immediately combines with something else. It's gone. So to deal with hydrogen, we have two hydrogen atoms coupled together, and then we have some oxygen, but we never have a single oxygen atom. If there's a single oxygen atom, it combines right away. So oxygen combines with itself. We have two oxygen atoms to give us one oxygen molecule. So we have H2, which is one hydrogen molecule, and O2, which is one oxygen molecule. But they only combine in the ratio of 2 to 1. So we need two hydrogen molecules, two H2 and one O2, and then we get two H2O. We get two water molecules out of this. And that's an example of something that Dalton discovered. There always are these simple whole number ratios that combine these atoms together to give us what we call chemical compounds. So that was huge. That was the first experimental evidence. I mean, the other thing to keep in mind is that undoubtedly many other people would do deep meditation and would go off and see things like hydrogen and oxygen molecules and electrons and so forth. The problem is they didn't have any framework to be able to describe what it was they were seeing. They look at it and say, that's nice. You know, it looks pretty. You know, I have no idea what it is. So we're trying to put together the framework for what in the world these observations are leading you to.
I just want to add, I would bet money that indigenous shamans were doing this.
Oh, yeah.
Everywhere.
Yeah, shamans in all ages were looking at these things. But they didn't, you know, they would have their own words, their own metaphors for describing these things. I'm just going to give you what the last 200 years of Western science has put together in this talk. So we'll take it from there.
But I think they saw them, you know, the way they see germ cells. They see it as an entity. You know, they see it in a very spiritual way.
Right.
They see it as living.
Yeah.
Which I just think that's really beautiful.
Yeah, they're undoubtedly, they see these things vibrating. They see them, you know, spinning around. They're not at all. We have these pictures from Western science, but they're static. But everything is really very dynamic and evolving.
That's a good word. Yeah,
over time. So the next person that we came to was Michael Faraday, who carried out a fundamental series of experiments that really suggested what was fundamental. He showed that electricity and magnetism were coupled together to one another. The thing that you're probably most familiar with that Faraday did was he took a bar magnet and put a piece of white paper over it and sprinkled iron filings on it, and then saw that the iron filings grouped together into clusters that started out at one pole of the magnet and went in coupling around in lines down to the other pole of the magnet. which suggests that there was some sort of magnetic field there between the North and the South pole of this magnet. And he also showed how there was a coupling between electricity and magnetism, that they're actually, if you will, different sides of the same coin. But the problem that he had, Faraday, was he wasn't the theoretician that he was the experimentalist. The experiments were great. Other people could duplicate them, but there was no underlying theory that he could come up with. The underlying theory actually came through this German, Hermann Grassmann, who did all this in 1845, no less, except that no one could understand what he did. He was so far ahead of his time, it wasn't even close. And I mentioned I was in graduate school, and I was asked to look at what he did here. And I came up with, you know, a recapitulation of what he did. But I noticed that his description of electromagnetism, what's down here is the new theory of electrodynamics, that it was all completely mathematical. There was no physics underlying it. It was just something that you would turn the crank and out would pop these equations. And I said, I wonder where the physics went. So, which we'll come to in a little bit. But it was, you know, even today, people, well, most physicists, you know, don't understand what Grassmann did. But the theoretician that put the stuff together was Maxwell in the 1860s, when he came up with a series of equations that summarize electricity and magnetism. And this is viewed as the second great unification in physics. The first one was due to Isaac Newton with gravity, where he explained that all of these masses that we have around us gravitationally attract one another, and the end result is that Newton came up with this theory that describes how planets run around the sun, and on and on. But Maxwell, one thing he did was he was looking at experiments from all kinds of people to do his theory, and he decided that there was something missing that would make the equations, if you will, symmetric. And in particular, he added a term that led to the possibility of having electric and magnetic fields moving through space as waves. Now, we use this today. We use it for our mobile phones. We use it for broadcasting television signals and so forth. So we're quite familiar with using this. But at the time, it was simply a proposal by a theoretician, Maxwell, but there was no evidence that this is what really happened. That you needed some experimental proof, which we're going to see in a second. The proof came about from someone in Germany, Heinrich Hertz, who carried out some experiments in 1887 and 1888. So notice it's already over 20 years after Maxwell has proposed his equations, and he was experimenting here with sparks. So he had he had what's called a dipole antenna. These are two pieces of wire, and there's a spark gap at the end where the two pieces of wire, and so he sparked it, and he had another dipole a little distance away, and all of a sudden he could see that he got a voltage and a current flowing on his other dipole. So he had a transmitter and a receiver with these sparks taking place, and this was the evidence that there were things called radio waves, and they were occurring in what would be called the high frequency range, hundreds of thousands of times per second, millions of times per second, in that sort of range. Now, this is something that Faraday never dealt with. He never he never had the ability to be able to go up into having things oscillating at these very high frequencies. But there was someone else who did. That was Nikola Tesla. Okay, so Tesla is known in part because he was a phenomenal experimentalist, but at the same time he was an incredible theoretician. So what he developed, he followed up on Faraday's idea of what's called an induction motor, where you have for example, a turbine that's spinning due to the fact that we've got a lot of water running through it from, say, a dam. So the turbine is spinning. We wrap a lot of coils around the turbine as it spins, and then we have some other coils right next to it, and those other coils generate electricity. And this is when Faraday came up with this observation experimentally, he was really excited. He thought this was going to be huge. And what had happened was a reporter went running up to him and asked him, well, why is this so great? And he says, I don't know why it's so great, but I do know that one day you're going to tax it. And the tax is what we pay for our electric bill every month. So that's who Tesla was. He invented basically the electric transmission system that we use all around us. And in particular, because he was an incredible experimentalist at the same time, he ended up looking at other things. And after he came up with this idea of this motor, which was in the late 1880s, he started looking at what Hertz had done and trying to generate signals in the millions of times per second, so very high frequency signals. And in doing this, he undoubtedly came up with what I'll call the theory of ether electromagnetism. So what is this theory that he probably came up with? Well, what happens is if you look at the equations for electromagnetism and you look at the equations for fluid mechanics, for flowing of fluids, they're actually identical. The only difference is that the equations for the flow of fluids include extra terms due to the density of the fluid. So if we say that, well, these electromagnetic waves that we're talking about here are carried by a fluid that we'll call the ether, okay, if there really is an ether here, then this leads to an additional set of terms beyond what Maxwell came up with for electromagnetism. And Tesla undoubtedly found these, and he started to play with them. And this allowed him to come up with all kinds of amazing things, which have all been suppressed for the last, since Tesla did this, okay? It's controlled by the black ops side of things of the different governments. Our government, the Russian government, the Chinese government are all aware of this. They refuse to let it get out there. One of the reasons why they suppress this is this would allow for example, to generate electric power, but at almost no cost. And that would allow us to have, for example, electric cars where we wouldn't need batteries. We would simply put these electric power generators in the cars, and that would destroy the economy because there would be no more oil and gas business. There would be no car business. There would be no banking business, and everything else that goes with it. But that's what happened. Tesla was clearly onto this. The other thing that Tesla did, just as an example, was in 1893, the city of Buffalo decided that they wanted to get electric power for lights for the streets for the city of Buffalo. And they had Niagara Falls 20 miles away. So they put out they requested different people. So both Edison and Tesla responded to their request to propose how you would go to Niagara Falls, generate electric power there, and then bring it into the city of Buffalo to handle the lights that were in the streets of the city of Buffalo. And Edison, being Edison, proposed doing this with DC power. So doing it with DC power, Edison required a regenerator every mile. He had 20 of them because it was 20 miles from Niagara Falls to the city of Buffalo. Tesla did it with AC, and in doing this, he required 3 regenerators, not 20. And so the city of Buffalo said, well, Tesla's got this thing. It only takes 3. We won't take that much money. We can try out. If it fails, we'll go with Edison. And sure enough, Tesla's thing works, but it made Edison the arch enemy forever for Tesla because he made a complete monkey out of him. He did with 3 substations what Edison required 20 substations, and it worked, and he made a fool of Edison. Edison was very disparaging of Tesla, but that was who Edison was. Tesla did all this by licensing his patents to the Westinghouse Electric Company that built this. He did one other thing at the same time. In the city of Chicago, they had the Columbian Exposition in 1892, 1893, and Westinghouse, in conjunction with Tesla, won the contract to provide all the electric lights at this exposition. And this, you have to go back in time and remember, there aren't any electric lights on the streets of any city anywhere. So here Tesla had taken this exposition and he put electric lights everywhere, and everyone could see, going there day and night. This is just incredible. And this really popularized deploying electric power throughout the world. Now, the other thing, not to disparage Tesla too much, was he started looking at X-rays, and he ended up. These are again a different sort of electromagnetic field. It's a different wavelength, but he ended up capturing an image using these X-rays. So he probably beat Wilhelm Röntgen, who announced in the discovery of X-rays. And the thing was that Röntgen had very crude imaging. Tesla, being Tesla, he's not only an experimentalist, but he's a theoretician. He ended up developing all kinds of extra improvements to the vacuum tubes that led to creating the X-rays, and he started sharing this stuff with Röntgen for X-rays, and so Röntgen ended up with much better pictures than he would have ever come up with on his own. So in return for doing all this, of course, Röntgen got the Nobel Prize in Physics. Tesla never got the Nobel Prize in Physics, but Tesla knew more than Röntgen about doing all this. As a different example of something that Tesla did, Tesla filed all kinds of patents for what is called amplitude modulation of electromagnetic signals. We would call this AM radio, or the same principles would apply for television, okay? So Tesla had all these patents filed years before an Italian, Marconi, set up a company that was able to transmit radio signals across the Atlantic. And Marconi said, look what I did. And Tesla took Marconi to court and won in the US Supreme Court, and had Marconi pay all kinds of damages for infringing on Tesla's patents. Tesla knew far more about what Marconi was doing than Marconi knew. Just to give you some idea, and these are things that Tesla's doing out of his hip pocket. He's just so far beyond the rest of these people. It's not even close. Okay, so now we're going to get back into the atom some more. We start to think that the atom has things called electrons associated with it. Different people like Faraday suspected that. They thought this electricity was tied up with the atom. There was a great English physicist, J.J. Thomson, who proposed that, well, these atoms, since we've got these cathode rays now that we're getting from Röntgen for X-rays and so forth, then what we have for the atoms is that the atom's probably a jelly of some sort, and it's got some positive charge in the jelly, and then the negative charge is around it to keep it so that it has overall a neutral charge. And it turns out he's completely dead wrong in doing this, but it just gives you some idea of what these physicists are thinking of for ideas. At the same time, here we have Charles Leadbeater and Annie Besant published a book in 1908 where they started describing their observations starting in 1894. So this is in the same time frame as Röntgen doing his X-rays, Tesla is doing what he's doing. You saw J.J. Thomson there. So Leadbeater and Besant published this book in 1908, and they simply went off to different museums around the world, and the museums would have on exhibit elements, things like here's a piece of pure carbon, here's a piece of pure iron, here's a piece of pure chlorine, okay? And they would just go there together, both of them, and they would meditate deeply, and they would both stare at this element, and they would come back with a picture that they would check each other on that suggested that the atoms that they saw under clairvoyance were basically a cloud of electrons around a nucleus. I mentioned before that you have to keep in mind the scale of the atom, that if we view the atom as the size of the Basilica of St. Peter's in Rome, then the nucleus is the size of the chalice on the altar in St. Peter's. It's 3 orders of magnitude smaller than the size of the atom. So we have this cloud of electrons, which are all negative, and then we have this nucleus, which consists of positively charged protons, and the protons have a positive charge, the electrons have a negative charge, so the overall atom has no charge to it. And in addition to that, each of the nuclei for these atoms has neutrons. So it turns out that for example, we take carbon. Carbon has 6 protons, 6 electrons, and 6 neutrons. And this leads to carbon having, because its nucleus has the bulk of the mass, the electron is 3/4 orders of magnitude less massive than the proton or the neutron. That if we take a look at 6 protons plus 6 neutrons, we have 12 in total. And that's what the chemists or physicists came up with as the atomic weight here to have a scale would be 12. But when they actually measured carbon, they discovered it was slightly more than 12. And they discovered that some of the atoms that they were dealing with, there was not simply 6 neutrons and 6 protons. Some of them had 7 protons and even 8 protons. 7 neutrons and 8 neutrons. And these are what are called isotopes. There are extra neutrons that are in there. And they're very small in number, typically, out of the total volume that we're dealing with. But the end result was it skewed the mass off from these nice integer numbers, like 12 for carbon, up to something that was, something higher than that. Now, Leadbeater and Besant were the first ones to observe these isotopes, the fact that these atoms have the same number of protons and electrons, but differing numbers of neutrons. And they also observed beyond this that each proton and each neutron has three smaller things, which are called quarks. They have three different types of quarks to make up a proton and a neutron. And then they looked at that in more detail, and they realized that each of the quarks is made up of three subquarks. But that's it. We finally reached the bottom. This is the end of the story. The basic constituents are that there's these subquarks are the basic elements, and Leadbeater and Besant called them universal physical atoms, or UPAs, but Western science calls them subquarks. Go figure. But this is what Democritus was talking about. He was correct. We have these subquarks that are there at the bottom of all this, and they're the basic building blocks of everything. Another key person here was Robert Millikan, who actually measured the charge on the electron, which was unknown until 1908. And it was a great experiment. He got the Nobel Prize for doing this. And he ended up, being able to use this in a variety of ways. But it just showed that, again, the electron was a key component, and it had a charge and it had a mass, and was fundamental to everything, just like Democritus said back, in 400 BC.
How did he supposedly come up with it?
How did Democritus?
Yeah.
No one knows.
Oh.
We don't have enough materials from Democritus. I should have asked Ron Cowan to go back and observe Democritus, to ask Democritus what was going on. What gave all of this away was this experiment by Ernest Rutherford in 1909, where he shot the nuclei of helium atoms into a gold foil, and and then he looked at how many went through, and most of them went right through. They showed that there was a lot of space there, as we said. There's a lot of space in the atoms, so things can go right through. But a number of these things bounced, or they hit some nuclei and they got scattered. And that's where he theorized that there was a very small nucleus there, and that this had most of the mass. And again, this got him the Nobel Prize for doing this. So there we go. We've got this picture of this atom starting to come together now. There's a Frenchman, Louis de Broglie, and he is, again, a theoretician. He's watching all of this work going on, and he looks at these electrons and he says, well, I bet that they also have wave properties as well. And in fact, I bet it isn't simply the electrons. I bet all these other things, these protons and neutrons and everything else, also have wave properties, okay? So everything is both a particle and a wave. And for this, he got the Nobel Prize in Physics, okay? This was actually demonstrated experimentally in 1927. But one of the things that he did as well was he was trying to explain the strange behavior of what was going on in all these experiments. And he said, there must be some sort of what he called pilot wave, something that was coordinating everything that's taking place out there. And this pilot wave model, everything is sending out a pilot wave to scan, to see what's going on. This was actually ignored, was felt to be a total boondoggle until 1952, when it was rediscovered and actually pushed much further by a great physicist, David Bohm. And what we'll see with the observations of Ron Cowan is that they're correct, that there is, in fact, an underlying information that coordinates everything. And that's why this computer model that we're dealing with here is going to be fundamental for describing, really what's going on. There's a lot more order than anyone realized. The thing that everyone knows is there's a thing called quantum mechanics, which is where you end up with the electrons being described as they run around the nuclei of these different atoms, and this was done for what I'll call the non-relativistic case, that is, things not running at the speed of light. But a Brit came up with a way to include it to go at any speed whatsoever. So he went beyond this, and both these guys got the Nobel Prize for their observations. But that was, if you will, taking you down a particular path. They didn't go down the path that I talked about of what Nikola Tesla did, of looking at the ether and its impact on electromagnetism, which we'll come back to. The French were active in this. So this is a couple. They're married. Irene Joliot-Curie and Frederick Joliot are married, and she was doing all this work, instrumentation, very precise lab techniques, and the two of them worked together and were able to come up with an estimate for the mass of the neutron. And one of the things that came up out of this was that if you took a neutron and just left it standing there in space, it would actually decay after about 5 or 10 minutes into a proton and an electron. And this was, amazing. No one had observed this before. And this was proposed to be the mechanism for creating these isotopes in all of the nuclei that we saw. Where did these neutrons come from? Well, some of them came from protons. Some of the things that happened was these neutrons would decay in the nucleus of these atoms, and all of a sudden we'd lose one neutron and have an extra positive charge, which would lead to a totally different element once we do this. So we go up to 1952 with David Bohm. David Bohm's doctoral advisor was Robert Oppenheimer. Bohm said, well, there's got to be some way to explain how all of these things interact with one another. What Schrödinger and Dirac did not explain this. And so he put together a theory for explaining this, which he called an implicate and an explicate order. So the explicate order is what we see, but there's an implicate order, that there's some coordination that takes place, which is actually algorithmic, or it evolves over time as a conscious whole. And this particular activity that he's talking about here is what led to Friedhof Capra writing his book, The Tao of Physics, in the early 1970s, and saying that we should follow theories like what David Bohm and de Broglie proposed, because it looks like they'll give us answers to things. And a lot of this will, he was willing to bet, would allow us to sync up with Eastern knowledge, with the Eastern mystics that were doing things. And that was why he called it Tao of Physics. The quarks.
That was one of the books that brought us together.
Right.
That we both read decades ago.
Right. Quarks, remember there's 3 quarks that make up a proton and another 3 quarks that make up a neutron. And 2 individuals came up with these notion of these quarks, and they were actually experimentally observed. No one has to date been able to observe these subquarks because the particle accelerators can't grow to those levels. But the thing to keep in mind here, as a result of all this activity, is we end up with, we ended up with a theory of gravity that Newton created, and that's one of the forces that physics deals with. And Einstein modified that to show that it was actually the curvature of space and time that was leading to what we call gravity, but it didn't contradict what Newton had done. We had the work on electromagnetism with Maxwell with his equations, and there was another Brit that I didn't talk about, Heaviside, who was able to popularize the stuff. We have the strong force. The strong force is what binds these quarks together to make up a proton or to make up a neutron. So this is, why in the world do we have a strong force? Well, if you think about the nucleus that we have there, I said that there's, a bunch of protons in it, and we know that in electromagnetism that like charges repel one another, and unlike charges attract one another. Well, the nucleus has a whole pile of positively charged protons in it. Why aren't they all repelling one another? Why aren't they all flying apart? It turns out that when you get to very short distances, what becomes a repulsion becomes an attraction. And this is what's called the strong force. The weak force was the one I talked about, where the proton would, the neutron would decay from a proton and an electron. And there was another little particle called a neutrino. So all of the forces of physics that have been discovered all come about under gravity, electromagnetism, the strong force that binds the nucleus together, and the weak force that allows the neutrons to decay. But in fact, you get all of these, as Nikola Tesla saw, and as the black ops guys know, out of a single theory of the ether with electromagnetism, which we'll come back to later on. So it's something that could have been done 100, in the 1890s, 1900s, but we never went down this road. The weak force I just touched on briefly, and here we end up with what's the triumph of modern physics as of 1975. Now, this leads to a bunch of things. You have an electron and a electron neutrino, and the electron and neutrino have these other two things here. These are actually resonances that the electron starts to vibrate much more quickly, and you get a muon, and it vibrates even more, you get a tau. So really, all of these are the same particle. They're the electron. The electron neutrino does the same thing. It starts to vibrate more, and you get these other particles. So there's really only one particle here, the electron, and one this neutrino. The quarks that are up here we have an up and a down quark, and there's some other types of quarks, but the quarks themselves obey a certain logic or algebra that goes with them. And then we have the forces here. So the forces are, for the electromagnetism, it's the photon. For gravity, for the strong force, it's the gluon. And then we have these other ones for the weak force. But notice that gravity doesn't show up here in this picture anywhere. In 2012, this Higgs boson was discovered experimentally. What is the Higgs boson? Well, it turns out that when the universe was created, that there's a mass for the electron, for the up-down quark, and so forth. And each of these masses is multiplied by the mass of the Higgs boson. The Higgs boson is a multiplier. So initially when the universe formed, there weren't any Higgs bosons, so nothing had any mass whatsoever. Everything was zero. Physicists love that. They call it totally symmetrical. But all of a sudden, as things started to expand, as the universe started to get created, then the Higgs boson came into existence. And the Higgs boson all of a sudden led to the mass being different for the electron, the neutron, the proton, the up and down quark. All of these things here all had different masses. One of the questions that comes up in physics is, where do these ratios come from? What in the world is going on here? We don't know. I asked Ron Cowan to go back and because of his ability at clairvoyance, to go back to the start of the universe here and observe, did he actually see a Higgs boson? And he did see a Higgs boson come into existence at the start of the universe. In fact, he saw two types of Higgs bosons. This is all for matter. All of this here is for matter. And there's a separate category called dark matter or transparent matter that physics doesn't know anything about. That's not in this picture here. And there's a separate Higgs boson for that. And we're going to come back to that next time when we discuss what Ron observed in doing that. But for right now, for the last 50 years, with the exception of the Higgs boson, this has been the state of physics. And all that's really happened is people have been able to measure things to 5 significant figures, then 6 significant figures, then 7 significant. So they know the mass, the charge, any property you could think of, the more and more significant figures. But there's been no fundamental advances beyond this picture here, which is what we're going to deal with in our next class. So what did Ron Cowan do? Starting in 1990s or so, and catch me on this, Bruce, this is just when Ron started to surface, and that was when he reached out to, there was a Brit, Stephen Phillips, who had categorized the work of Leadbeater and Besant, and was very excited over their work and observations that they'd done. And Ron Cowan, in the 1990 timeframe, contacted Stephen Phillips in the UK, and he said that he had been able to duplicate the observations of Leadbeater and Besant, and in fact, he'd been able to go far beyond what they'd done. So in particular, what Ron had done was he actually observed what is called here as dark matter as well as matter. Leadbeater and Besant never observed dark matter to the best of our knowledge. Ron observed that all of these things that we call electrons, protons, and everything else, even the compartments of space itself, are all covered with blocks of information. And the information is always constantly scanning. And when it detects a change in anything around us, then it ends up reacting. It has a set of algorithms, which are the laws of the universe, that describe how it ought to react. So this is what de Broglie and David Bohm were talking about. This is the pilot wave that's there that coordinates everything. It goes to the ends of the universe. The scans that are taking place are done with some sort of radiation that we can't explain right now. We don't know what it is. It's not in any theory that we've talked about. Ron was also able to observe what Leadbeater and Besant observed, these subquarks, and he saw that for matter had 10 strings that, for example, enclosed an electron, but the 10 strings that enclosed the electron were really just having resonant energy inside there. The strings were just vibrating like crazy, and the electron, even though we thought it was a particle, was really a piece of jelly that was an energy field. And the same thing was for dark matter. Instead of 10 strings, it was 5 strings. So the matter that we have vibrates much more because there are 10 strings rather than 5 strings. Dark matter doesn't vibrate nearly as much. Ron observed the neutrinos, the photons, and the gravitons, the particles that manage gravity, which are things that were not observed to the best of our knowledge by Leadbeater and Besant. He also went down and looked at space itself and saw that space was in fact made up of a foam, that space is discrete. It's a set of compartments that hold these particles, and the compartments are all coated with these blocks of information. Ron observed the start of the universe was the bounce from the previous universe. And the previous universe was contracting, 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 and then it bounced, and that created this universe. So he observed that. Leadbeater and Besant didn't do that. And that's where he observed these Higgs bosons for matter and dark matter being there. And then the key thing that we'll spend time on is the fact that we have more than just 3 space dimensions and 1 time dimension. In fact, we actually live in a 26-dimensional space, which is kind of mind-blowing. You'd say, what, where in the world does 26 come from? But these are all things that Ron observed. And this brings us up to the present. In 2020, a really outstanding physicist, Stephen Wolfram, began exploring computers and algorithms in the 1980s, and built up a incredible company called the company's called Wolfram after him, but he has a whole series of software packages. So the company's doing hundreds of millions of dollars a year in selling and supporting the software. And he's been using the profits from this to continue to do research into fundamental theoretical physics. And he's convinced that, and I think he's on the right path, that what's going on here with the universe that we see around us is that all of these algorithms that Ron Cowan observed, that are everywhere, that they're governing everything around us. And he chooses to call this the Ruliad, or the rule of rules, or the rule of information rules all, and so forth. So that's what we're going to be ending up covering when we start to go through the next class. So let's see. One of the things that you'll come up with when you deal with all this stuff from modern Western physics is there's certain things that they don't talk about. So we talked about having this description in quantum mechanics for things in the very small, but notice there's no description of gravitation here, which is something that occurs in the very large. It occurs, with planets and stars, for example, as being a significant force. And in particular, this is what led physicists to say, well, what we need to do is come up with some experiments where the phenomena, what occurs on the very small level, which is the quantum effects that they're talking about, is the same as scale as with gravitation. Well, one place where that occurs is at the start of the universe. That's where this bounce occurs, and everything is in a small little area. And the only problem is, how do you do an experiment where you start up the universe again? It's not the easiest experiment to go around. But that's an example of what's going on. A different thing here is that string theory in physics is one of these theories where it sounds interesting until you realize that, first of all, there's no equations whatsoever that anyone has written down for string theory, as in 0. The next thing is that they think it takes place in 10 or 11 dimensions, but we live in 3 dimensions for space and 1 for time. So why do they need all these extra dimensions? And then the real thing that they never want to talk about is that after 500 years of study, Western science has now realized they've been studying 5% of the universe, and the remaining 95% is made up of what's called dark energy and dark matter. So you should think of this as with the maps that Columbus supposedly had, where the world ended and there was this edge of the earth where there were dragons and everything else was over there, and no one knew what was going on. So this is not a minor screw up. When you can't explain 95% of the universe after all of this time, you better believe that the best and the brightest are working on this night and day. And what Ron did was he provided a lot of insight into what this was going to be. But of course, they don't buy into meditation as a way to go carry out controlled experiments. Okay, it's not something that's plausible for Western science. Plus, Ron is doing all this with paper and pencil. He's doing sketches of what he sees. Well, where's the instruments? This is paper and pencil. What are you talking about? And so it goes. There's other things here we're going to touch on in not just the next class, but in other classes. There's a notion of synchronicity that occurs here. So we have, I mentioned this, I think, briefly, that you have these events that occur that appear to have no causal relationship, but they're synchronous with one another. So a very well-known one was there was a great theoretical physicist named Wolfgang Pauli, and Pauli was awarded the Nobel Prize because he came up with a theory for the neutrino. The thing that Pauli had was all kinds of experimental physicists wanted to have Pauli come to visit their labs. They wanted to show him his experiments, and maybe Pauli would suggest some other experiments they could do that would push them in new directions they didn't realize. So Pauli loved to go to these labs to see the experiments. So whenever he went into a lab for another physicist, the experiment would fail. It would collapse. And they called this the Pauli phenomenon. No one knew what in the world was going on, including Pauli. And the most well-known example of this was that this one physicist in Germany knew that Pauli was in Zurich, Switzerland. And all of a sudden, his experiment failed totally. But he knew that Pauli was in Switzerland. So what in the world was going on? And a few days later, he got a postcard from Pauli saying, oh, I was on a train going from Switzerland to Denmark, and I was actually going through right by your university. And that was exactly when the guy's experiment failed. And so forth. So it just shows you that there's things here that people have trouble reconciling. Another dimension to all of this is the notion of consciousness and what is consciousness, and we'll touch on that as we start to go into this, and then later on we'll come back to this and look on the very large scale, what's called cosmology and the birth and death of the universe, which appears to have happened many times and will continue to happen. And we're going to reconcile all that as we get into this. So these are just examples of some open issues that are, just mind-boggling that, so little can be said about them. We'll do our best, but you judge for yourself whether we're remotely on. So that's that. Let me get out of screen sharing here.
Oh, excuse me.
I'll send out the handout there. You'll see that. I'm trying to think what else is there.
Any questions?
Yeah, we're going to cover next time what Ron Cowan did and Leadbeater and Besant in more detail. So you'll see, they were, no matter how you measure it, they're way ahead of what current physics is doing. But again, it's done with Eastern techniques, with meditation and these special skills. If you go into the Yoga Sutras and you read, remember there's 195 sutras, and they're broken out into 4 books. So book 1, which is the one that most people are familiar with, deals with how to center yourself through both breathing exercises and postures, so that you can get away from all of the noise and distractions of everything around you, and come into the realization of what's really going on around you, and the loss of self, that everything is linked to everything else. And in book 3, they say, by the way, there are these other little things you can pick up along the way, such as this thing I talked about for clairvoyance. It's like a sideshow, okay? That's not the point of meditation. The point of meditation is to focus on love and compassion, and especially for yourself and for others. But oh, by the way, you can look down into the nucleus of atoms, and you can look out into the far reaches of space, thousands of light years away. And if you, for example, are able to raise your vibration, whatever the statement means, which we'll come back to, if you raise your vibration, then you can do things like walk through walls. Because remember, the atoms have a lot of space to them, okay? Then the nuclei are where they're at. That's most of the mass, but most of it is just these clouds of electrons. So if you raise your vibrations, you can just walk right through a wall, okay? Because you're vibrating at a different level, and you're just walking through the space. End of story. And people have done this. There's examples of in Marco Polo with his travels from Italy to China, to Kublai Khan, that he ended up on the Silk Road, and he stopped at one watering hole there, and the sheik that was there had two swamis, and they were both sitting there levitating 3 feet off the ground. You can go read it. And Marco Polo was sitting there looking at all this, going, "What's going on?" He says, "Well, they're just sitting there, and they just decided to lift off." But there's an example in the Western literature of around 1300 AD of some Catholic priest who started flying around over the church in the town he was in and over all the houses, okay, levitating. He prayed so much that he ended up levitating. And these things all get suppressed, okay? We don't want to hear this. This is ridiculous, and so forth. So that's what we cover here. We cover the things, we'll see what's going on. So this is crash course in modern Western science, but we're going to now go into the Eastern version of the Western science and what Ron Cowan did. And you'll see he's suggesting a lot of very interesting directions that would lead to an incredible new life for all of us. It'd be a very different life. I don't know why you would have a car. You just have one of these flying saucers, and you go zip around in it. End of story. Why have roads? So anyway, that's where we're at.
Sounds like the end of Back to.
What is this? You don't want to end with
I
that?
said that sounds like the last line in that likes the last line in Back to the Future. There
Yeah.
are no roads. Like
Yeah.
I have a question. Having blown our minds with of the science context is, you're doing the science, you're going to come in with the Eastern. Is this sort of the end result, is where modern Western science meets Eastern
Well, yeah. The
mysticism
reality
and
is,
like
yeah,
theology?
the Western science has gone too far toward materialism, okay, and the notion of spirituality, having souls, okay. I remember I said everything was energy, everything. So the electron is a bunch of strings, but it resonates, and there's some energy inside there that gives us the electron. Well, the same energy can be able to create a spiritual being, an entity, okay? But it's missing. I showed you the picture of what Western science thinks it's all about. There's a whole bigger picture, which is encompassing the spirituality side of it. And the spirits are going to be what are also immortal. They're going to be souls that will live forever. They will reincarnate with bodies and come and go. But the spirits are going to be the things that will be key toward all of these things, and that'll be energy. And that's what's missing from the picture here. plus the environment that we're in. I just touched upon space by itself, but space is what we're in. And so what does that mean? You'll see as we get into this, but I'm just trying to lead you into this where we're going. I'm not trying to do anything other than that. Make it plausible that there really is a story here that's of incredible order and beauty, and people like Ron chose to really dig into this. And I was lucky enough to be able to work with him and suggest to him, the framework for I'm just throwing back the framework that Western science has developed, which is still got a long way to go. If remember, the framework only covers 5% of the universe. That's not a minor,
So
thing. It's great what they did for 500 years, but we can do better, and that's what's going to happen in the you'll see in the next chunk of time.
And I would say very definitely a thesis of ours is that the West needs to look to the East. And to indigenous cultures.
That's what David Bohm, if you go look on YouTube, you'll find some great videos. David Bohm actually went to India and spent time with a bunch of Eastern mystics trying to understand what it was they were talking about, because he realized that Western science was not making any advances. And they needed new ideas. And that's why Fritjof Capra wrote the book, The Tao of Physics. He said physics is going to hit the wall unless you reach out to the East for new ideas. And of course, that didn't happen.
It's really, I think, a question of the paradigm that they're clinging to.
Yeah,
they're looking at all of it, and it's just too static. It's too fixed.
There's a poll that was taken of all of most academics. Which do you value more, your reputation or the truth? The reputation won by a landslide. Okay, so if you start to come up with things that are this far out of the box, you get blackballed, you get thrown out. People think, you're a kook, but yet these are where the ideas come from. When Max Planck, who did the real fundamental work in quantum physics, where he started to show that in fact there was phenomena there that the earlier physics couldn't possibly explain. Someone asked him, well, what was it like when you started to go out to all these universities and lecture? I mean, how did you succeed in doing this? And he said, oh, it's very simple. I needed one funeral at a time. I had to wait for each of these Herr Doctor professors to die off at this university and that university, and then I had new students there, and they would listen to this and go run with it, and they realized what I was talking about was correct. But it was hopeless to persuade the people that are there. Forget it. And that's what you're faced with.
But it seems that what you're saying boils down to energy and wave motion and energy. And you're saying that a soul is no different than these other units of energy that we've talked about. So within that context, then, if we have all these souls and all this energy, how would you define God? Or maybe that's a question for another
what I
class.
would define as God, it's not a male person with a long beard wearing a robe.
You're breaking up.
On a throne. That's not what I would, what I would define it as. Let me go back to our have to go back to our Aleph talks. Okay, hold on one sec. I think I'm there. Okay, can you see this? This is the resources
periodic
tab on the Aleph Talks website. So when I go down here, okay, this is, oh, phooey, hold on. See,
Slide this whole thing over to the left. The window.
slide,
This window, the big window.
slide this one.
Yeah,
I don't think I can.
you have to grab it up at the top. Yeah.
There we go. Okay. This is what Ron Cowan observed, okay? So these blocks of information, and so he showed a picture here. So here's a block of information, here's another block. But he looked at one of the blocks, and the blocks are actually a whole stack of information. So this picture is a little misleading. And that covers, here's a picture of an electron. That covers the outside of the electron. It's completely covered these information blocks. So the electron has this information in there. This is always scanning every which way. And when it detects a change, then it goes into the algorithms that are there, and it says, okay, then I have to do this, whatever this is. That's so you would say, who is God? Well, I didn't come up with this. Okay, this is the control mechanism that whatever God is put in place. But God came up with this picture, and he said the only way for me to make this thing work, and this is what Ron Cowan observed, is I need 26 dimensions to make it work. And you know, this you're looking at, this is not, you know, a house painter. This is a Picasso. This is off the charts in terms of trying to figure out how to do this. So this picture here we're showing where the matter is in 10-dimensional space, but right next to it is another 10-dimensional space. This is where your guardians are, your archangels. Okay, they're right next to you, but it's in a different 10-dimensional space. And we'll go through this in more pictures next time, but this is remember, the space is itself covered with the information blocks. Okay, so I didn't come up with this. I'm simply observing this.
We liken it to the movie The Matrix, where there's those lines of code raining down.
Yeah, we're talking to this outfit about having that on our website. Okay, if you could see this website, you'd see little lines of trickling down here on the website all the time as a background.
We had a snow.
So all that information, is that sort of like Jung's concept of a collective unconscious?
Yes.
Yes. Yeah. Yeah. This is what. Much. Yeah. We want to be. Yeah. I mean, I'll give you a different example. Okay, because we want to be having as many cross checks as we can with what's going on. Okay. So just to show you here, there's these extra dimensions here that are, here's the three space and one time that we're in. Here's the 3 space and 1 time that our soul, our guardians are in. That's over here right next to us. So there's another 18 dimensions here. Okay, 6, 6, and 6. Okay, but notice they're clustered into 3. This is where Jesus had his consciousness live. This is where the Holy Ghost lived, and this is where what you would call God lived, the most enlightened of all of these things. There's a Trinity sitting right here staring at you. Okay, if you don't like that, then you'll love this. There's 3 holes here in the 6-dimensional space. This is not your normal 6-dimensional space. There's 4 holes here, and there's and there's 8 holes here, and they're in this.
Holes? What do you mean?
I mean exactly what I mean. It's a hole. Hold
It's like
on.
a wormhole in
It's
Star Trek.
going to connect from one dimension to another.
Oh, okay, okay.
So here's an example of what it is. This is a picture by this guy in Seattle, Chihuly. Okay, showing this thing. Let me go back up here. I think I missed it.
We were thinking of having a chandelier designed for the church.
It would go into the foyer.
That might.
That's very cool.
Here's
a little bit like a
a
COVID.
two-dimensional picture of a six-dimensional Calabi-Yau manifold. Okay, but this is just, you know, it's just a two-dimensional slice of 6 dimensions. But you can see there's holes in this thing. Okay, and this thing is evolving. It's spinning. Okay, so what happens down here?
That's a still from an animation.
Yeah, there is an anime. I don't think I put the animation on the website, but where I'm heading, what is this? There's 18 dimensions here. Okay, if there's 3 holes here, I'll connect those 3 holes to the 6 dimensions over here, which is, and this has 4 holes, so I connect them over here. And this has that takes care of 7 of the 8 holes that are here. So I'll connect out of these 6 dimensions. I'll connect 2 of the dimensions together. Now all the holes are connected. Everything else. Well, I have 18 dimensions, and I have eight things connecting them. I really only have a 10-dimensional space, but a 10-dimensional space is what the Kabbalists saw in the Tree of Life. It was the 10 Sephiroth that were there. They observed these spaces as the 10 nodes. There were 3 lower nodes and then 7 higher nodes that made up what they call the Tree of Life. And you know, you keep looking for checks like this to see what's going on. I mentioned that there's 3 holes here. Okay, there's 3 holes here. Well, I also touched on the fact that in the standard model, the electron had 2 other resonances. The reason why it has 2 resonances is because there are 3 holes here. There's one for the electron and 2 more for these other particles, and so it goes. So there's a lot of, we're going to come back to this. I'm just trying to sketch for you why it's plausible, but I'm not trying to. I'm just trying to paint the stage for this is where we're at in you know, October of 2023.
I'm starting to follow. I mean, you're basically talking about energy, whether it's spiritual energy or physics energy.
Right, and that's what we
Got
said
it.
in the very first lecture. Einstein said everything is energy. He didn't say everything was mass.
Right.
He said everything was energy. It's just that some of the energy could be kind of squishy, kind of jelly-like, or pretty hard. So it looks like a particle, but it's still energy.
It's the rates of motion and the patterns.
Yeah,
It's moving in patterns.
yeah.
That have to do like those tables that just went by of the elements.
Yeah.
Those are
The thing that's amazing about
one way
these
of looking
pictures
at the pattern.
is these things are vibrating at incredible speeds. Okay, Ron Cowan was able to stop this stuff. Okay, it isn't he simply was looking in the microcosm. He stopped it from vibrating so he could make these sketches. And that's what Leadbeater and Besant did. So there's more than just clairvoyance. There's your ability to reach out and stop an electron from vibrating. I can't do that. So anyway, more to follow. This is it for tonight.
I
This is Western physics
up
for
all the
last.
question time. Did questions?
But yeah, no. What if you've got questions? Well, we'll answer them in the next lecture, guaranteed. And there's a lot of
Well, I
stuff here.
wouldn't guarantee them that answer.
Yeah,
Yeah, I was worried about the guarantee as well.
yeah. All we'll promise in
little
this
ambitious.
class is that your ignorance will be on a higher level.
Yes. Okay. Hmm.
Thank
I
you.
think that's true of anybody, any of the
Yeah.
geniuses would say that. I think Einstein would say that. I think
Yeah.
Pauli would say that.
Yeah,
The mystery gets
even
deeper and
Tesla
deeper,
said he
right.
didn't understand this stuff, and he was, no one knows how smart he was. So,
They asked Einstein once, "What's it like to be the smartest man on the planet?" And he said, "I don't know. You'd have to ask Nikola Tesla."
yeah, Einstein, when he developed his theory of general relativity, he lectured on it all over the planet, and in particular, he went to New York City and Tesla City in row 1, and Tesla is listening to the whole talk by Einstein, and he goes up to Einstein after, he says, this is really beautiful. It's just, totally irrelevant, but it's just a wonderful, piece of math that you've done. It has nothing to do with what's really going on. Then Einstein started to realize, what does Tesla know? A lot more than he thought.
But Einstein was absolutely a mystic,
Yeah.
and knew it, and said it.
Yeah, look at our first class with the. Let me go back there to that. So we're not.
He said all of his ideas came to him through his intuition, and then he'd work out the math afterwards, which he really didn't like doing. But the ideas were intuitive and I think very visual, and almost like visions.
Right. Here, I'm just going to go back to our resources tab. So see, you can check me on this. Here it is. Here's the overview lecture, and here's the what is God. And so this is what we did. And, here's what Einstein said concerning matter. We've been all wrong. What we call matter is energy, whose vibration has been so lowered as to be perceptible to our senses. Matter is spirit reduced to the point of visibility. There is no matter. This is not me saying this. This is Einstein. Time does not exist. We invented it. We'll come back to that. That's how to explain the synchronicity. But it just shows you how little we know.
Yeah.
So with that, have a wonderful weekend. And any questions, send them along. We'll see what we can do. We're pulling together stuff for the next class, like I finished doing this at around 10 to 7. Okay.
You can blow our minds again.
Well, we're just trying to give you your money's worth for the class. That's all.
And we're going to be talking at some point about Mercury retrograde and how that relates to the double slit experiment. With we know it's an illusion that it's not going retrograde. It's just from our perspective. But why is it, why is there the synchronicity with it? And so we've been germinating some ideas, and I have 2 parts of that on the website, 2 of 3, and part 3 is yet to come, but that's something we want to work on.
Yep.
Is the interface of consciousness with the phenomenon, and that seems to be part of physics. It seems to be a really integral part.
Yeah, and this is very Eastern.
And the particles seem to have awareness. They seem to have some kind of consciousness.
No, things like rocks. Rocks have awareness.
That's part of the scanning that goes on. But this is what the scientists are saying. It's not, we're not making it up. It's what the experiments seem to be showing.
Yeah. So
Oh,
anyway,
onward
and upward. Have a wonderful weekend. Bye-bye.
thank you.
Bye.